This is a mechanical energy conservation scenario. We have a curved ramp that our cart is going to roll down. It starts at rest here at moment 1, just as it's about to begin moving. Here at moment 2, it loses contact with the ramp and launches, becoming a projectile. It's going to launch at a 60-degree angle there. And moment 3 will be when the cart is at the apex of its parabolic path, the high point. We have some given information, the mass and the heights of the center of mass of the cart at moments 1 and 2 above our vertical reference point, y equals 0 down here. And we would like to solve for the following: the speed at moment 2, speed at moment 3, and the height of the cart at moment 3. Let's think first about the energy transfer going on during this story. From moment 1 to 2, we're going to be converting gravitational potential energy into kinetic energy. Specifically, the force of gravity is going to be doing the work that converts gravitational potential into kinetic energy. The normal force is around, but not doing any work. It's just a bystander. Then beyond the low points here, gravity is going to start converting some of that kinetic energy back into gravitational potential as we move back up. So beyond that low point, and when we reach moment 2, gravity will be doing negative work, converting kinetic energy back into gravitational potential. Normal force still not doing anything, not doing any work. At moment 3, when the cart goes past its high point, at that one instant, gravity is not doing any work, but it's about to start converting gravitational potential back into kinetic energy via positive work. And the normal force is not even present at moment 3. That's not there at all anymore once we've lost contact with the ramp. Okay, so that energy transfer is going on, but do we even need to use energy principles to solve for these unknowns? The question is, how do you, as a problem solver, know that you should be applying energy principles? Why not just go back to dynamics? Let's think for a moment. Could we use our known skills with Newton's second law and the constant acceleration equations from kinematics to solve for the speed here at moment 2 with this given info? So pause the video for a moment here and consider, could you use a dynamics and kinematics based approach to solve for the speed there, and why or why not? Pause the video. Got it? The answer is no. Our track is curved, which means that the free body diagram is going to be changing from moment to moment. And if the FBD is changing every moment, then the forces in N2L are changing every moment, which means the acceleration of the cart is changing from moment to moment on that curved track. The acceleration is not constant. Here's the free body diagram at one particular moment on the ramp, but as the cart moves, those forces are going to be tilting and changing. We can set up N2L at any given moment, but it's not that helpful because the acceleration we solve for at this moment will be different in the next moment, and we can't use those constant acceleration equations. So a curved ramp is a perfect case for using an energy-based approach instead. That's what we'll do. Once you've decided to use an energy-based approach to solve your problem, then decide what to include in the system and write an expression for the mechanical energy of the system at each important moment. So at each moment, consider, is the object moving? If it is, it has kinetic energy. At each moment, consider, is the object above or below the reference point? If it is either above or below, it has gravitational potential energy. So here at moment 1, we have no kinetic because we're starting at rest, but we do have gravitational potential because we are not at the reference point. We're at a height above it, y1. At moment 2, we are moving, so we have kinetic energy, and we are above the reference point, so we have gravitational potential. Same thing at moment 3 here. We are moving, so we have kinetic energy, and we have gravitational potential because we are above the reference point. All right, so we can write an expression for the energy of our system at each of those moments. And now we want to decide how these mechanical energies at these 3 different moments are related to each other. Are they equal to each other? Are they not equal to each other? Here's how we figure that out. Let's start with our energy conservation principle and consider the interval from 1 to 2. We're trying to find the speed here at moment 2, so let's consider what we know about this part of the story as the cart moves from 1 to 2. You ask yourself, are there any non-conservative forces present over that time period? And the answer here is yes, we do have a non-conservative force present, that normal force. The normal force on the cart from the curved track, that is a non-conservative force. It is there. So that's potentially a concern because non-conservative forces, when they do work, they change the energy of a system. So we ask ourselves, is that normal force actually doing work from moment 1 to 2? And we've already decided no, because the normal force is perpendicular to the velocity at all those times. So the normal force is not doing any work. The angle between the velocity and the normal force would be a right angle because the velocity is always parallel to the path and the normal force is always perpendicular to the path. So there's a right angle there. We already decided this or knew this when we recognized that the normal force was just going to be a bystander force not doing work during our story here. And so, since we've decided that the normal force is not doing any work, that means there is no work done by non-conservative forces from moments 1 to 2, which means the change in mechanical energy of the system from 1 to 2 is 0, which means our initial mechanical energy, E1, equals our final mechanical energy, E2. And so we're going to accept this expression for E1 equal to this expression for E2. So we write down K1 plus UG1 equals K2 plus UG2, and then sub in our specific expressions, mgy1, 1/2 mv2 squared, and mgy2. 0 is our initial kinetic energy. And this is an equation that we now want to rearrange algebraically to solve for V2. We'll get our speed at that moment. To do some simplifying here, we recognize that there is a mass on every single term here. And so we could factor out those masses on the right-hand side and then cancel them with the mass on the left-hand side. All those masses are going to cancel. And this is a key point. If your mechanical energy only includes kinetic and gravitational potential terms, that is, if there's no spring potential, no elastic potential energy term, and energy is being conserved, that is, there's no work being done by non-conservative forces, then mass is going to cancel out in that equation, and the motion will be independent of mass. When there's only K and UG, mass is always going to cancel out. So the mass of the object turns out not to matter. It doesn't affect the outcome. Our final speed will have nothing to do with whatever the mass of the cart is. So even though the mass was a given piece of information, we didn't need that given piece of information. And in fact, we could have solved for V2. We can solve for V2 even if we do not know the mass of the cart here. That's a situation to be on the lookout for in the future. It comes up fairly frequently. So let's just do the algebra from here on out. We're going to move the GY2 term over, multiply both sides by that factor of 2, then factor out a g here to get this, square root both sides to get this expression for our speed at moment 2, plug in our numerical values for g and y1 and y2, which were given to find our speed at moment 2. Okay, that's our answer using a standard conservation of energy-based approach. This would be the sequence of steps that you write down to show your process for solving that problem. But I want to now show you an alternate method, an alternative approach to the problem, an alternative solution. We'll get the same answer just through a slightly different route. Instead of using our conservation of energy equation, we could have instead started with the work energy theorem, which is often just as good. So here we'll state the work energy theorem, and the left-hand side will be the sum of all the works, that is the works done by every force. And let's consider our time interval from 1 to 2. I'm also going to show you a different way of labeling your work on the page. Note that in our previous approach, I kept writing underneath delta E and underneath the work, the interval 1 to 2 to let the reader know that you were considering that part of the story. Instead of writing 1 to 2, the interval underneath those terms, just another way of labeling it for the reader's benefit is to put a little label off to the side like this, indicate that we are now talking about this part of the story. And there is a force of gravity during that time. There's a normal force during that time. So the work that they do will add up to be the net work. We've decided already that there's no work done by the normal force from 1 to 2. So the delta K is just equal to the work done by gravity. And that is a conservative force. We know that the work done by a conservative force equals the opposite of the change in the corresponding potential energy. So you can replace WG with minus delta UG here. And looking at this expression, it reminds us of our energy transfer scenario, that the force of gravity is going to be transferring gravitational potential energy into kinetic energy as the cart rolls down the ramp, and then kinetic back into potential as it rolls up the ramp a little bit, while the normal force hangs out, not doing any work. So there's our energy transfer represented algebraically. We'll replace delta UG with mg delta y. Delta y is y final minus y initial. Delta K is K final minus K initial. K initial was 0 because we started at rest up there at moment 1. Here we're going to plug in 1 FmV squared for K2, and we see mass cancels at that stage. I've distributed that minus sign to flip these two terms, and we can rearrange this to solve for V2, and we get the same expression for V2 using this work energy theorem based approach as we got here from our conservation of mechanical energy based approach. We get to the same place either way. Using the alternative approach here, I think in considering the work done by gravity, it invites us to consider that path independence property that the work done by conservative forces has. Path independence means that our result here, this resulting speed, does not depend on the shape of the track. Our cart started here and followed this roughly black curved path to get from moment 1 to 2. But note that our algebra here didn't have any information about the actual shape of the path. It just required us to know y1 and y2. So a path that could have had any other shape, a track with any of these other shapes to get from 1 to 2, would have resulted in this same final speed. Same final speed no matter what the shape of the track was. It only mattered where we started and where we ended. And in fact, if we had started the cart here, if this had been our moment 1 and it had just dropped straight downwards, just fallen vertically from moment 1 to 2, so that it had the same delta y along this path as it would have along any of those paths, well, the same delta y means the same change in gravitational potential energy, which means the same work done by gravity. So this cart also would have had the same final speed at moment 2 as the cart released from this ramp up here. So that's a valuable conceptual point. These two carts released from the same height would both have the same speed by the time they got here, no matter what the shape of the path they took. They'll have the same speed when they get down here, but that doesn't mean they'll get here at the same time. The shape of the path will affect the time it takes, the travel time. Of course, the cart falling straight down is going to get to this location much faster than the cart rolling down some curved ramp. But when they both get here, they'll get here with the same speed because of that path independence of the work done by gravity.